Alright, you take left. Come on. I'm gonna throw a flashbang. Alright, go, go, go. Oh, hold up. Hello? Oh, hey, John. Oh, you're going hunting? Cool. Where? Alright, I'll meet you there in 30 minutes. See you. Falconry is the ancient sport of training and hunting with raptors. Here we see a peregrine falcon in a stoop, or its signature dive. In this position, with its wings tucked in, it becomes the fastest animal on Earth. Clocking up to 250 miles per hour, this peregrine falcon has its eyes set on a pigeon, its prey. We're going to discuss the physics of how a peregrine hunts, and specifically we're going to look at a problem that examines how far a peregrine lands from its impact point. Okay. So what happened in the hunt was this peregrine falcon stoops down at an angle and collides with the pigeon, which is traveling horizontally. And then together they travel off as one body as a projectile following a parabolic path to the floor. We're going to figure out where the peregrine and pigeon landed. And to do that, we're going to use our kinematic equations. Delta y is equal to 1/2 at squared plus vi yt, and then use that to solve for t, so we can plug that in to the equation delta x is equal to vxt. These work in principle because the kinematics account for the time taken to fall, and the time taken to fall is the same for both x and y components. And since the x velocity stays constant throughout a flight, or fall, then we know that it's constant and can be used in the simple d equals rt equation modified here. Okay, so what the factors that we know are delta y. The peregrine and pigeon are flying at 200 meters above the ground when the collision happens. And then acceleration is just acceleration of gravity, negative 9.8 meters per second squared. And we can assume that stays constant because the peregrine falcon does not spread her wings until she reaches near ground level. And then what we don't know is velocity, or time, since that's what we're solving for. So to find velocity, we're going to have to use a different set of equations, and that's the momentum. Now we set this up as a conservation of momentum problem. By the law of conservation of momentum, we know that pi is equal to pf, and also m1v1 is equal to m2v2. However, in this case, since we have a perfectly inelastic collision involving two bodies, and one of them is moving in at an angle, the peregrine falcon, then we set this up as a system of equations regarding the x component of momentum and the y component of momentum. Then to do this, we just set it up like so: m1 of the peregrine falcon times the vx component plus m2v2, the pigeon's momentum originally, and the sum of those is equal to the sum of the masses times the x component of the final velocity. And then here, we can see that there's only one component on this side, and that's the peregrine falcon, because the pigeon does not have a y component of velocity at first. And then so, just m1 times the vy component is equal to the sum of the masses of the peregrine and the pigeon times the y component of the final velocity. So what we know is mass of peregrine falcon, mass of pigeon, and the velocities. And then, so here we have the velocities of the peregrine and the pigeon. The pigeon is traveling horizontally at 33.5 meters per second. That's its maximum speed, and presumably what it's flying at. The velocity of the peregrine falcon, however, is clocked in at 200 miles per hour. But we need to use dimensional analysis to convert that to meters per second, and that is 89.41 meters per second. As we can see here, this is a drawing of the velocity vector and its components. And then so we solve for Vy, and we get 77.4 meters per second, and Vx 44.7 meters per second. And we just use trig to do that. The angle appears 30 degrees. Then, so this is adjacent opposite hypotenuse, and use the trig relations. Now that we have established what we are looking for and what we have, we can rearrange our system of equations to solve for theta and VF. So the way we're doing this is just some simple algebra. We're isolating VF so that we can plug it into the other equation, the y equation, and then basically this is what we get, and that equals sine theta f. And since we're solving for theta, we can move that term, which also has a theta, to the other side. Then we get sine theta over cosine theta, and get that's tan theta. And then we inverse tan it. And all of that comes out to about 54.19 degrees for theta. Then using theta, we plug it back in to the equation to find VF. And I just plugged it into that top equation right there. And VF comes out to be 71.6 meters per second. So now that we figured out the velocity of the combined peregrine-pigeon mass, we go back to our kinematic equations. And using this velocity, we find its x and y components, which we'll then plug into these two equations. Now here, I've solved for the components already, and I've just used trig ratios to determine which is which. Okay, going back to these equations, now we just plug them in, and then for the delta y is equal to 1/2 at squared plus vit equation, we rearrange to get a quadratic equation, so then we can use the quadratic formula to solve for t, which turns out to be 14.64 seconds. Now using that, we plug that into delta x is equal to vxt, and multiplying the velocity and time, we get 613.16 meters.